Hi everyone, this is Konstantin Petrov with Artilux in Jubei City, Taiwan. I will be presenting our company's view on where the automotive range-finding technology is going and the rationale for the technology solution that we offer as a company. Before I begin, I would like to thank the organizers for this opportunity to speak on a hot topic. I assume that most of you are no strangers to the word LiDAR. Some of you may know it casually, others perhaps professionally, and some may even know ins and outs of it in great technical detail. My purpose here is not to be technical, but rather to convey an idea, a vision, our vision as a company. When it comes to the word LiDAR, for the record, personally, I'm not a great fan of it. I grew up in the days when the radar was relatively new and cool. So I see the word LiDAR as laying claim to the original glory while being the same in principle, only operating at much shorter wavelengths of the electromagnetic spectrum, with some specific differences, of course, in the way electromagnetic radiation is produced and detected. The LiDAR sends out laser pulses, waits for them to come back, measures the delay time, and computes the distance. And this here is its typical modern-day incarnation, a point-and-click pocket rangefinder. It is not new. In the old days, it used to be this bulky, expensive, gun-shaped contraption a police officer would use on a freeway. But nowadays, it is much more compact and inexpensive and very common. Construction workers, for example, carry these things every day. You can get it for under $50 on Amazon. It's just another tool nowadays. But here we are in this seminar talking about it because it has found new significance to self-driving cars. The allure of the self-driving car is here, has been here for a while. It holds this promise of safer personal travel and more economic transportation of goods and cargo. It holds the promise of big economic impact. And because of this, significant resources and money are being thrown at its development. Many talented minds, many big egos, all compete and race for the technological superiority and bragging rights in this new emerging field. On the one hand, the truly reliable driverless experience is still far away. On the other hand, there is an emerging consensus among the developers, and the consensus is that the driverless car will need a LiDAR, and not just one, most likely several of them. And it would work on the same principle as that pocket rangefinder from Amazon, but in a much more demanding and sophisticated application, of course. As opposed to measuring distance to one point, we now need a bigger picture. We need to map the scene, as it is called, and quickly. To that end, the old laser rangefinder has been evolving. It began as a point-and-click handheld device, something a police officer would aim at a speeding car. But a LiDAR in a self-driving car needs to measure many more points, and quickly so. That led to the emergence of rangefinders with mechanically scanned multiple detector arrays. And while that was a solution, it had obvious drawbacks. No one is thrilled about having these bulky, rapidly spinning mechanical things, especially when they're fragile, especially when they're expensive, and especially when they're easily knocked out of alignment, which leads to measurement errors, especially at long range, and requires frequent calibration. So eventually, MEMS devices came to the scene. They came to the rescue. With these micro-electromechanical silicon devices, the beam scanning still remains, as the name implies, mechanical, but in a much more rugged, compact, and elegant way. You could even say that these are electronically scanned devices, and that would be correct. Being small and stiff, they're much more tolerant to shock and vibration. So for the vehicle LiDAR, that was a significant breakthrough. There are actually other types of solid-state scanning mechanisms, such as optical phase arrays, without any moving parts at all. And we can talk more about those offline. Nevertheless, most of the MEMS devices still operate at near-infrared wavelengths, so laser power has to be kept low for eye safety. And that makes it difficult to measure long distances. The semiconductor laser industry, for its part, hasn't been standing still and began to catch up with the demand. Lasers at longer wavelengths began to appear and delivered more power. The retina of the human eye absorbs less at shorter wavelengths, so you can safely shine more power out onto the scene to provide higher resolution at longer distances. This LiDAR evolution, as shown in the simple chart, was always driven by application requirements. For the self-driving car, the requirements are many, they are complex, there's a whole long list of them. Some requirements are purely technical, others are about safety, still others are about reliability, and others are economic, having to do with manufacturability and cost. Here are some of the more important technical requirements arranged in color-coded groups. The elements in each group are bound by a mutual trade-off. The first trade-off, for example, is quite easy to understand. The LiDAR measures distance by waiting for the light to travel to the target and back. The longer the distance, the longer the wait. In a self-driving car, we want to see the big picture. It is quite literally big. In our desire to know what lies far ahead, we reach for longer and longer distances for better awareness of the scene, so we have more time to make better driving decisions. And of course, we want details. We want many, many data points or pixels in our field of view. You could see now that for a LiDAR, with a single beam and a single detector, this becomes a bandwidth problem. The longer the distance, and the more pixels you have in your field of view, the slower the frame rate, the slower things are happening. And another trade-off group here is cost. See, just like it is in life with money, there are ways to avoid or beat some of the trade-offs by using multiple detectors, for example, so-called the multi-channel approach. However, to measure longer distances and with large enough number of pixels, especially when you're doing it all in parallel, you tend to need more optical power. But that optical power must still be eye-safe. You can't just blast the scene with all the laser power you can buy, because there are people out there, including in places very close to the rangefinder. And it must be safe there for them, safe for their eyes, everywhere, both at close range and far away. This is where longer wavelengths come in, about 1.3 to 1.5 microns, where the retina in the human eye doesn't absorb as much. But if you want to operate at long wavelengths, you have to pay more, because long wavelength detectors use different materials and cost more than silicon. Silicon can only detect up to about 1 micron. So we find ourselves in a dilemma whether we either make unpleasant trade-offs or pay more money, which is unpleasant too. This is where we, Artilux, come in as a company. We propose to address all these trade-offs simultaneously by introducing the first CMOS-based germanium silicon sensing technology, years in the making. It addresses these LiDAR trade-offs in a way that is both economical and scalable to volume, and has the required performance. In the context of the now familiar performance matrix, it all looks like this. We take care of the bandwidth trade-off by going to a sufficiently large two-dimensional array of germanium silicon detectors. We already have considerable experience doing this. And we take care of the range versus resolution trade-off by going to long wavelength lasers, whose eye-safe output power is higher, by nearly an order of magnitude. And finally, we sidestep the cost penalties merely by staying with the current manufacturing technology, the 12-inch germanium silicon wafer. This here is a one-page equivalent of our company's name card, so to speak, but in a much simpler form, of course. We champion the 12-inch wafer-scale germanium silicon technology, whereby innovative germanium-based light detectors are integrated with silicon CMOS devices. That way, you can see things at long wavelengths, and then condition the signals and process the data using the full power and performance of today's CMOS under large-scale integration. This is an optoelectronic platform that is naturally high speed and naturally scalable to large two-dimensional arrays. And it is mature enough to be used in mobile time-of-flight cameras already today. By combining this sensor technology with an adequate transmitter at 1.5 microns, something we are working on with our partners, we will transition to measuring longer distances for use in LiDARs in self-driving cars. In other words, we propose killing 3 birds with 1 stone. And in the light of what I have been explaining here, it is merely a natural extension of what we have been doing all along. Germanium silicon detector arrays combined with adequate long wavelength laser sources. It is quite simply a logical path to a LiDAR, and the transition has already begun. Because of the time constraints, I cannot talk in much detail about the technology or any of the variations we've been working on, so please feel free to contact us at our website. Thank you.